Hello, everybody. My name is Brandt Bucher, and today I'm going to be talking about basically how Python executes your code and how a bunch of us have been making that faster in recent years. So buckle up. Before we get started, a little bit about me. So my name is Brandt Bucher. I first started using Python when I was studying computer engineering as an undergrad at UC Irvine, and I never looked back. So I gave up hardware and I was all in on software because I just loved the language so much. I started contributing my first code pretty quickly after that, and I've been involved in Python core development since about 2020. My pandemic project was adding structural pattern matching to the language. Shortly after, I joined Microsoft's faster CPython team, or the CPython performance engineering team, where I work now, and we've just been focused on making the reference implementation of Python, CPython, faster for everybody. Our work quickly bore fruit, so in 3.11, we were able to show a 25%-ish speed improvement over the 3.10 interpreter, and in recent years, we've been working on actually adding a JIT compiler to CPython, which has been a big, fun, exciting, really challenging project. And so I'm going to share a little bit about that today. So what is Microsoft's CPython performance engineering team? You may have heard of it referred to as the Faster CPython project. This is a larger initiative that is spearheaded by the 6 of us at Microsoft who are on the core team, but we collaborate with people all over the world. So in addition to the people on our team, we also work with people at Snowflake, ARM, and also the National University of Singapore. And you know, it's not a closed team or anything, so if anyone wants to get involved, there's a lot of really, really cool stuff that we're working on. So if anything seems interesting today, please reach out and get involved because it's really, really exciting work, and it is an opportunity to have like a serious impact on real code. All of our work happens in the open, so all the people on my immediate team are committers to the CPython code base. We have a repository on GitHub called fastercpython/ideas. This is our public issue tracker. While we use the CPython main issue tracker for works in progress, this is kind of where we just kind of throw ideas out for early discussion and share papers and things like that. So enough about me and my team. What is Python? Well, Python is this programming language that is older than me. It's very high level. It's very widely used. It is a dynamic, interpreted, object-oriented language that features automatic memory management and a bunch of deep introspection and metaprogramming features. So all of these things are making life very, very nice as a Python programmer because you can do a lot, but you also don't need to do a lot. But as language implementers looking at this, this is terrifying, right? Like all of these things that make Python so easy to use and so successful are also the sort of things that make it very, very difficult to optimize effectively. Specifically, just to give some ideas, most objects, as with many dynamic programming languages, most objects have arbitrary mappings of attributes, and these are actually exposed as dictionaries at runtime. And they don't just need to be string attributes, these are normal dictionaries. You can throw anything in there. You can store references to them, you can monkey patch them at runtime. It's a nightmare. Bytecode itself is a runtime object, and people do crazy things with this, building their own code objects or introspecting existing code objects. Frames themselves are runtime objects, and you would not believe what it is possible to do with a running Python frame. You can assign into the locals, yes, but you can also change the line that is currently executing. This is how like the jump command works in a debugger. You can jump in and out of dead code. Even attribute and global name accesses and even stores to local variables can execute arbitrary code. So reasoning about the state of the world is really, really difficult to do, even in limited context. And even simple operators go through incredibly complex double dispatching. If you think you know how Python's operator resolution works, I can almost guarantee you that you're missing some details of how it actually works. Like if subclassing isn't part of that mental model, then it's wrong. And finally, as I mentioned, a debugger can be entered anywhere and basically do anything. So this is kind of the context we're working in. And again, this is all great to see as a Python programmer because you can do all sorts of crazy things and debugging your code is really, really powerful and easy. But at the same time, for the language implementers, yeah, these features are like kind of fun or whatever to expose to users. But when it comes time to actually have performant implementations, it's actually really, really difficult to make any progress, especially on something that's this widely used and this old. So that's Python as an actual programming language. Let's talk about CPython, though. CPython is the reference implementation of CPython. It's written in C, which is where the name comes from. And it's used by the vast majority of Python programmers, so much so that for the rest of this talk, I'm just going to use the terms Python and CPython interchangeably. It is reference counted, augmented with cyclic stop the world GC. This is relevant because people have become very, very used to and reliant upon the prompt reclamation of acyclic garbage. And it has an incredibly rich ecosystem of third-party C extensions, for example, NumPy and Cython and other libraries like that, things that we cannot break, or if we break, we need to provide clear upgrade paths. It's maintained by a few dozen active core developers. I'm lucky enough to be one of the few who's actually paid to work on CPython full-time, but for most people, it's either a retirement project or nights and weekends. Maintenance is also a concern because we have a finite amount of developer time, and it's very, very valuable. And of course, Python, specifically CPython, is free and open source, so you can check out the code here on GitHub, and there's a full issue tracker where all the actual work in progress happens. So with that context, let's talk about optimizations. So typically when you are optimizing a programming language, the steps look like this. First, you build an intermediate representation, then you check the types, you optimize based on those types, and then you compile. Obviously, for dynamic languages, this type checking step needs to be replaced with a profiling step. This is something that we've been doing for a very long time to optimize languages like JavaScript. And so this is just-in-time compilation, right? And it means deferring a lot of the traditional compiler optimizations until actual runtime rather than statically and ahead of time. So a lot of the kind of traditional optimizations that we're used to seeing, while some of them can be applied in sort of limited measures to the actual static bytecode itself here on the left, many of these actually just need to be deferred till runtime to actually be of any use. And even amongst the ones that we can do statically in the bytecode compiler, even for things like dead code elimination, again, it's very, very limited because debuggers can jump into dead code and they can assign to local variables on any line. So even propagating constants is like super fraught. So again, this basically means that we need like very clear runtime context in order to build anything that's performant at all. So we're just going to walk through basically how recent versions of CPython have actually executed my Fibonacci function here. This is a iterative Fibonacci function. It's pretty straightforward. We basically take a parameter n, assign local variables a and b to be 0 and 1. We loop n times, and we're just adding a and b together repeatedly. Specifically, we're going to focus on this hot inner loop where the function spends most of its time. So the bytecode for this loop looks something like this, which I'll show in the center, and then we'll just walk through how this executes. As many of us know, CPython is a stack-based virtual machine, so I'm going to show the stack there on the far right. So when we enter this loop, we start with an iterator already on the stack. And basically, this first instruction in the bytecode stream, the for iter instruction, is responsible for advancing the iterator and pushing the result to the stack. So this is a somewhat generic operation, and there are lots of generic operations in Python because it is so dynamic. So things like iteration, attribute lookups, method calls, even normal operators can follow many, many different code paths and do many, many different things. You can have an add operator that formats your hard drive if you really want to. In this case, there are lots of different things that we can iterate over. And so that's where specialized bytecode comes in. And this is where we were able to get a lot of the performance improvements that we saw in 3.11. Basically, like I said, there are many things that we can iterate over. We could be iterating over lists or tuples or generators or a custom iterator object. But a very common thing for people to iterate over, and what we're iterating over in this case, is a range object. And so we actually have a bytecode specialization for for-iter range. And the way specialized bytecode works is basically these generic instructions at runtime will listen to the types that they're operating upon and replace themselves with self-modifying code, basically replace the bytecode instructions in place with a specialized variant. This contains a couple of guards to make sure that the assumptions hold, in this case to check that we're still iterating over a range object, and then it contains a fast path for actually doing the work. And in this case, the work can be a lot faster because we don't actually have to go through all the dispatching involved in Python's iterator protocol. And so basically, after that's done, we store the result in the fast local variable, in this case, just the underscore. And then we load 3 more fast local variables and push them onto the stack, B, A, and B again. Then we hit our binary operator instruction, which is responsible for adding these 2 values together. Again, things like addition are incredibly kind of complex in the way that they actually dispatch at runtime. In this case, we're just adding 2 integers together, and so we will specialize for the common case of binary op add int. So this is something we can do a lot more efficiently. Now, it's important to realize that this specialization actually adapts to the code over time. So as the program undergoes phase shifts or the context in which the program is running changes, the specializations will adapt too. And this is really important, and we'll see why later. But just to give you an idea, if I were to enter a debugger inside of this loop and replace A and B with strings, for instance, this is no longer integer math. This is now string math. And so the guards that actually check that the specialized instruction is operating on integers will repeatedly fail. And after doing so for a small period of time, the instruction will respecialize itself into, in this case, binary op add Unicode. And so you can see that sort of as your program undergoes shifts, the bytecode actually adapts and changes with it. And specialization is super cheap, since a lot of the work that we're doing to figure out which specialization we should use was already going to happen in order to dispatch the operation itself. It's almost free. So we specialize the second time any bytecode instruction is hit. Basically, in our mind, there's run never code, run once code, and run many code. So specialization is cheap enough that it just makes sense to do. So finally, after we have added our 2 integers together, because we haven't entered a debugging session, at least not yet, we pop 2 results off the stack and store them in fast local variables. And by then, we hit the bottom of the loop, the jump backward instruction, and we're back to the top. So basically, that is how Python has executed for quite some time now, a couple of years, ever since we landed specialization in 3.11. But where we're going with this is basically higher tiers of optimization. In this case, what we call micro-op traces. So basically, our goal is to build a tracing JIT compiler. And we've already made some really great progress towards that. So what are micro-ops? Well, to give you a little bit of background, we've made a recent change in the last couple of years for how Python's interpreter is actually defined. Previously, we had a bunch of handwritten, like actual cases in a big C switch statement. Recently, we've made the change to actually generate all of those cases from a DSL. And that frees us from a lot of the kind of tedious work of actually needing to do all of the bookkeeping of like adjusting the stack itself or pushing and popping items from the stack and doing like frame pointer updates and, instruction pointer updates on the frame and things like that. So to give you an idea of what that looks like, this binary op add int instruction in our DSL is actually defined as the concatenation of 3 other operations. In this case, it's first guarding that the top of stack item is an integer, so we have a micro-op for that. Guarding that the next item on the stack is an integer, so we have a guard for that. And then finally, the meat of the instruction, binary op add int, which actually pops those 2 values from the stack, adds them together, checks for error, decrements their reference counts, and then pushes the result. Again, you can see that I've sort of had this declarative form where I say what the stack effect of an instruction is, and so all of that is generated automatically. Now this is nice because when generating the binary op add int instruction, we just sort of concatenate the bodies here. But it also means that we now know the different components of the instruction. In addition to this, we also get nice code reuse because it should be pretty clear that the 2 guard instructions can be useful for other instructions as well. For example, if I'm multiplying 2 integers or subtracting 2 integers, we can use these same ops. So while we are actually generating the bytecode interpreter itself from this DSL, we're also statically analyzing the DSL, and we can use that to generate a lot of additional metadata. So for example, a table that maps the base bytecode instructions to their component micro-ops. And we can do this for every single instruction. And this makes translation of our collected traces to kind of a lower level, more optimizable IR completely automatic. So you can see here that once we've projected our trace through the loop, it's just a matter of basically walking over our trace and looking up each instruction in this table that we've already generated automatically and basically just concatenating all of the implementations together. And so this is really nice, and so it happens very easily and very cheaply. And one thing I forgot to mention is that when we project the trace through the loop, we're actually stopping the program and basically looking ahead and seeing, okay, where are we actually going to go? So we're not recording a trace as the interpreter is running, we're instead stopping and following it. It's at this point that we do some basic inlining. Since our call specializations have information about where we're actually calling to, inlining becomes pretty simple. And we also keep track of the most recently seen directions of branches so that we can follow branches through the trace. Again, in our Fibonacci example, it's just a straight trace through the loop, but it's nice because we just get this sort of inlining and branch tracking for just based on the profiling data that we are already collecting. So once I have this micro-op trace, we actually want to do something with it, right? Starting in 3.14, which is due out in October of next year and is currently in active development, we start optimizing these traces. And we have a basic optimizer that's in place now. And it performs some sort of lightweight optimizations, but our plan is to really build upon this in the coming year to do more kind of meaningful transformations. So just to give you an idea of sort of what we currently do and what we hope to do, we do a number of passes over this linear sequence of micro-ops. But sort of the most interesting and the most powerful of these is an abstract interpretation. This abstract interpreter that we loop over the micro-ops is, you guessed it, generated from that exact same DSL. So we are actually able to generate the abstract interpreter and have default cases for many of the instructions, and we can handwrite cases for the ones that we want to optimize more aggressively, which is great for developer productivity. So you can see here that we'll basically just loop over each of the instructions, and we can keep track of sort of the symbolic values of what we're operating on. As we encounter things like guards, we can narrow the types of stacks and locals, and we can even keep track of sort of what different expressions that we have encountered along the way. It's during this that the current implementation will do some like lightweight guard removal. So if we're guarding the same value twice, we can remove it. We also promote some like global loads and local variables to constants at this point, and we remove some ref counts. But again, a lot of this is still in the early stages, and we hope to do more aggressive stuff later. So at this point, in addition to those changes, we have another pass that will basically do a lightweight escape analysis and remove some bookkeeping that's unnecessary. For example, to check that our optimizations are still valid, or to set the instruction pointer on the frame if we might escape and need to be able to form a trace back or something like that. But again, in the future, we hope to do more powerful things. One kind of just obvious example would be being able to identify guards and hoist them out of the loop. So that way they're not in the actual hot path, which again allows us to reduce bookkeeping even further. So once we have that optimized micro-op trace, basically the way that we handle tiering up from the base interpreter into our new micro-ops is, again, using specialization. So in this case, we can take our jump backward instruction and specialize it into an instruction that we call enter executor, which will basically start executing our optimized trace of tier 2 micro-ops. So how does this do? Well, obviously, we don't want to interpret these things long term, but we do have an interpreter for them, just because we needed to have something working to make sure that everything works correctly and that we can debug it. So actually, when you enable the micro-op interpreter, and after all the optimizations that we already perform, it's about 20% slower, which is like a huge letdown, right? Like we've got all this work, we've got like the beginnings of some cool optimizations, but a big part of that is that we're introducing a ton of interpretive overhead. You'll notice that the trace of micro-ops that I was left with was actually much, much longer than the original trace of bytecode instructions that I had. And the bytecode instructions are already specialized. In addition, the name micro-op is sort of deceptive because these instructions are way, way huger than the base bytecode instructions. They contain much wider operands and cached values, and they have much more like debugging information and de-optimization information. So decoding them is actually a lot more complicated. In addition, there's a lot more of them, so the interpreter loop itself is a lot branchier and more complex. So that naturally drives us towards just-in-time compilation, which is where we were kind of headed the entire time anyways, but is now even more justified than before because we don't want to do all this work and then now get a 20% slowdown. So to recap, we have a couple of technical goals that we hope to achieve with this. Basically, we want to remove the interpretive overhead that we've introduced with the micro-op format, and we want to statically compile these optimized traces. And this is being done for a couple of different reasons. Basically, we want to reduce indirection by burning in constants and caches and arguments and things into the machine code itself rather than having to decode it in this interpreter. And we want to move data off of frames and into registers. If you noticed, the micro-op format doesn't actually change representation at all. We're still pushing and popping things from a stack and storing and loading things from local variables. Finally, we want to bring hot code paths in line. So rather than having a generic interpreter with a bunch of cases that are kind of in a tangled control flow graph, we'd rather unroll that into a linear sequence of code. Now, given the context that we're working within with CPython, we also have a couple of realistic goals about what we can accomplish, right? So in order to set ourselves up for success, in order for this to be feasible for CPython, we need to have broad platform support. Python is very widely used, and it's widely used in a lot of different places by a lot of different people. I don't think it would be necessarily successful if this JIT compiler were only able to work on 1 or 2 operating systems or on 1 hardware architecture. In addition, we want to have as few runtime dependencies as possible. Currently, if you download a Python interpreter from python.org, everything just works. You don't need to also install a compiler toolchain nearby or build LLVM or whatever for your weird platform. And finally, and most importantly to me, it needs to have low implementation complexity. Like I said, Python is overwhelmingly maintained by volunteers, and so maintainer time is very, very valuable. We're willing to leave peak performance on the table in order to have something that's maintainable and that people can feel confident fixing bugs in and extending into the future. And when adding language features, it's not a significant time sink for them. So again, these are very much in conflict, right? Like, we want to be able to make things faster, but we also are kind of tying our own hands behind our backs with the situation that we find ourselves in. And so one sort of really satisfying solution to these sort of competing goals is this thing called copy and patch compilation. It comes out of this paper from Stanford by some very creative people who also have great taste in keynote speakers. If you want to read the paper, then I highly recommend it. There's also a great accompanying blog post by one of the paper's authors, Haoran Su. It walks through basically using this copy and patch technique to build a JIT for a Lua implementation. So if you don't know how just-in-time compilers works, read that blog post. You'll know how JITs work. But in a nutshell, it's a way of automatically turning a C interpreter into a fast template JIT compiler. We have a C interpreter, we want a JIT, sounds promising. Even more promising are the numbers quoted in the paper. Compared to a WebAssembly baseline compiler, in this case Liftoff, copy and patch has been observed to have 5 times faster code generation and about 50% faster code overall. So not only are we JITting code faster, the code that is being JITted is faster as well. So it's strictly better. Compared to a traditional JIT toolchain, for example, LLVM with a low optimization level to keep things snappy, it's 100 times faster code generation and still faster code overall. And finally, as sort of an upper bound on the sort of performance that you can expect from this sort of thing, compared to an optimizing JIT with handwritten assembly, in this case Lua JIT, a copy and patch Lua implementation has been observed to be faster on some benchmarks and only about 35% slower overall when you take all benchmarks together. So this is exactly what I'm talking about when I'm saying we're willing to leave some peak performance on the table in exchange for what seems to be a great JIT implementation. So how does this work? The idea is really, really cool. Basically, I'll start by asking a question. If you have a sequence of bytecode instructions and you want to translate them to machine code as quickly as possible, how would you go about doing that? Well, it might look something like this. At runtime, you walk over your sequence of bytecode instructions, and then for each one, you copy some static precompiled machine code into executable memory, and then you patch up instructions that need to have runtime data encoded in them. So this would be things like jump targets or operands, that sort of thing. Now, when you look at these 2 steps, you'll realize that this sounds a lot like something that we already have, which are relocatable object files. So I could just as easily say, when linking or loading an ELF file, first I want to copy some static precompiled machine code into executable memory, and then I want to patch up the instructions that have the runtime data encoded in them. In this case, these would be extern relocations, relocation records for symbols that you're linking against. And so the way copy and patch works is pretty elegant. Basically, if we're starting with the case for our load fast micro-op here, the instruction itself is pretty straightforward. We basically pull the local off of the frame by indexing into its locals array with our oparg. We increment the reference count of the value that we're loading, and then we push it to the stack. We want to compile this instruction in isolation to machine code automatically. This is how we do that. Basically, we take the body of that instruction and we put it inside of its own C file, inside of kind of a dummy function that we're going to throw into a C compiler. Now, obviously, this isn't going to compile on its own. We're accessing local variables that don't exist. For instance, we need to get the frame from somewhere. Now, the frame isn't like some sort of constant. It's going to be different every single time that our JITted instruction executes. So we actually probably want this thing in a register. Thankfully, we can kind of force it into a register by just saying, oh, it's a parameter to the function. And so when we enter this block of machine code representing the body of the function, it will expect the frame to be in that register. You can kind of see where I'm going with this. Similarly, the stack pointer. This is just like the frame. It's going to be different every single time that our code executes. And so we can throw that in a register as well. However, with the oparg, we have something a little bit different. The oparg is going to be effectively constant each time we JIT the code, but we don't really know it when we're building the template itself. So the way copy and patch actually handles this is by just sort of saying, OK, let's just magically insert the oparg there and move on. So let's just ignore the problem for now. Similarly, you'll notice that we need some way of basically transferring control flow to the next instruction in the trace. So again, we're just going to hand wave that away and just say, OK, we just have some way to magically run the next micro-op. We'll just call into the next micro-op at the end of the function. So how do we deal with these two kind of hand-wavy placeholders that we put in here? Well, as I've alluded to, we can actually use externs to do this. So by declaring both of these extern, basically what the C compiler is going to do is it is going to leave holes in the generated code where the information needs to be patched, and it will actually give us relocation records that say where those holes are and exactly how to patch them. So you'll notice that I have my oparg here, and a hole will be left for that. And then we also have the call to the next instruction, which here is expressed as a continuation. You'll see we have that must-tail attribute, which is a unique feature of Clang. I think GCC supports it now too, I think because of us. But it's really nice because it basically guarantees that rather than being a call, this will be compiled to a jump. It basically guarantees that you'll get a tail call here, which we need for correctness. So if you take this thing and throw it into your compiler, what you'll get is an ELF file that looks like this. And this has everything that we need to JIT our load fast instruction. It has all of the bytes that we want to copy. So you can see here they're highlighted in blue. And it has all of the holes that we want to patch, highlighted in red here. And at the bottom, our relocation records tell us exactly where those holes are and how to fill them. Now, we could just move on with this as it is here, but we actually have the opportunity to do some very localized optimizations. So we don't want to be handwriting huge amounts of machine code, but when we see opportunities to improve the quality of the machine code in very clear and simple ways, we'll absolutely take advantage of that. So for instance, you'll see here that where we're loading the oparg, we're actually doing so through a layer of indirection. That's because we need to load a wide 64-bit value for our relocation, but really the oparg will be able to fit in 32 bits just because of our micro-op format. So we can actually relax this load. Instead of using an indirect load to get 64 bits, we can just encode 32 bits in the immediate. This is a very standard sort of a load relaxation that things like linkers perform. Basically, at runtime, if something can be encoded more efficiently, different transforms like this are very well documented. Similarly, we have this jump to the continuation at the very end of the instruction. This is a full 64-bit indirect jump, which is a little bit overkill because we know that the jump that we are going to make is going to be nearby in the code. So we can make this a 32-bit immediate jump instead. Similarly, you can see that after those transformations, we've introduced two no-op instructions at the very end and very end of the trace, so those can be removed as well without too much worry. And finally, we now have this zero-length jump at the end of the trace. Remember, when we're actually emitting the machine code itself, we're going to lay out one instruction directly after the other. So this jump to the next instruction is going to be a zero-length jump, and we can just wipe it out safely. And so once we have that, we can actually just parse out all of this information and basically write it into a static C header file and generate this function here. This is a function that if you call it, you can JIT a load fast instruction. All you need to do is pass it a buffer and the instruction so that it can retrieve the op arg. This is really, really cool, and it's really, really fast. It actually takes more time to allocate the memory for a copy and patch JIT compiler than it does to JIT the memory itself. It's awesome. So another really, really great part of this strategy is that it has incredible platform support, because we're able to build on, or we're basically able to outsource all of our kind of nitty-gritty, low-level optimizations to a optimizing C compiler at build time, in this case LLVM. Another thing I forgot to mention is that when we are compiling these templates, we can do so with a very high optimization level, because we're not bound by runtime constraints. So in addition to x86-64 on all the platforms that we care about, we even support 32-bit Windows and 64-bit ARM on all of those same platforms. This is pretty much most of the places that Python runs. There are some more esoteric platforms, but these are absolutely the most common ones. And we can just support them out of the box with very little implementation effort on our part, basically just knowing how to translate those relocations. And so let's talk about the results. And again, these are sort of intermediate results, because a lot of this work is ongoing. And we just recently landed the JIT compiler earlier this year. The current implementation has about 1,000 lines of build time Python code. So this is the code that handles actually taking all of the micro ops, putting them into sort of those dummy C functions, compiling them, parsing out the ELF, fixing up the assembly, and then writing it out into that C header file that we include when compiling the main interpreter. This is accompanied by about 100 lines of complex C. This is basically just a template for that dummy function that we sort of insert the opcode bodies into. And there is an LLVM dependency, but again, this is a build time dependency, not a runtime one. So users don't need to have this installed on their machine. It's only if you are building a Python interpreter, which is much less common, with the JIT enabled. At runtime, things are super slick. We have about 400 lines of simple C for the JIT loop itself. It's basically just looping over the instructions, allocating the memory, and calling each of these generated functions, one for each instruction. And we do have about 4,000 lines, and I should mention that C code is like simple, but it's like simple-ish, because JIT is never simple, right? We also have about 4,000 lines of truly simple generated C, and it really is just as simple as the code that I showed you on the previous slide. It's these function bodies that basically perform a mem copy and then a couple of basically writes into a buffer of bytes. And most importantly, no runtime dependencies. And so you can see here that we have taken all of this complexity and we've shifted it from runtime into build time, which we're absolutely happy to do, and out of C code and into Python code, which we like writing a lot more than C code. In terms of the results of the JIT itself so far, you'll remember that when we had the micro-op interpreter enabled with the light optimizations that we already perform, it's about a 20% slowdown. With the sole change that rather than interpreting the micro-ops, we JIT them, we are now back at parity with the base level interpreter. And we're not even doing most of the fun stuff that we hope to do. A big reason why we haven't actually focused work on improving the JIT code itself, and I'll get to some of our plans for that, but a big part of why we haven't actually focused work on that itself is because currently our tracing implementation needs a little bit of work. According to statistics gathering, we only run about 6% of our benchmark code in the JIT. So obviously, if we were to make the JIT twice as fast, it would barely show up on the headline number, right? And this number is actually kind of lower in practice because our benchmarks only spend about a third of their time in the interpreter loop anyways. They spend a lot of time in GC and library code and stuff. So we needed to get this number up. As of today, this number is more like 65%. So we've been putting a lot of effort into making sure that we can basically detect and translate more types of hot code at runtime. And by the end of the year, we're on track to get this to about 91% with the handling of a couple more edge cases. Now, another interesting number is the amount of memory overhead, right? So when we first landed the JIT and we were JITting 6% of the code, we had about 10% increase in total memory usage at runtime. Now that we're JITting 10 times as much code, memory usage is half that. So some of the people that we've been collaborating with, specifically at Snowflake and ARM, have been working on actually improving the memory usage of our JIT code. And the results are actually quite dramatic. And the really cool thing is that this is actually sort of a high watermark, because this is based on benchmarks which have a high ratio of code to data. In most situations where you would actually be experiencing memory pressure, you would have a high ratio of data to code, and so this number would actually matter less, since more data doesn't mean more JIT code. So with that in mind, let's talk about future work. Where are we heading and what are we working on? Most of this is for stuff that's going to ship in 3.14 at the earliest. 3.13 just came out, I think, last week, so it's stable. Go download it, go try it. But 3.14 is where we're kind of focused now. So one thing that we're interested in is this idea of stack caching. And this comes out of a paper from about 30 years ago, but the idea still holds pretty well. It's basically a lightweight register allocation scheme for stack machines. So you'll notice that in our micro-ops, we are still actually incurring a ton of memory traffic to send data to frames and pull data off of frames, and those live out on the heap. So ideally, we would like to put as much stuff in registers as possible, because register allocation is a very important optimization. While we're able to rely on LLVM to do good register allocation within the body of a single micro-op, it's kind of on us to make sure that the information that flows between micro-ops is treated appropriately, rather than it just being sent to and from memory whenever we decide we want to read it. So you'll see here that for my binary op add int instruction, we are basically just pulling two values off of the stack, adding them together, checking for error, decrementing the reference counts, and then storing the result to the stack and shrinking the stack. And you can see here that we're actually doing a lot of work on the stack pointer itself. Again, this isn't like the hardware stack. This is just a Python heap allocation sitting out in memory somewhere. So we want to reduce this as much as possible. Now, we've already kind of hinted at this, that when we want things to be in registers, we can actually just represent them as parameters to the function. So let's say that we want to cache the top of stack value in a register, which in this case would be a parameter that we take in from the function and pass to the continuation. We can now automatically generate two versions of this binary op add int instruction. One where the cache is empty, in which case the way we get our inputs doesn't change, but now we actually don't need to write the result back to the stack. We can just pass it to the continuation in the appropriate parameter there at the bottom. And then we can also generate a version where the cache is populated by a previous instruction. And so in this case, we're actually able to get one of the operands from the register, get the other one from the stack, and then write the result out to a register. And it's easy to see how this extends. We have lots of registers to play with, and so, for instance, we can have a cache state with two items, in which case the frame isn't involved at all. We take in both of our values as cached values, and then we send them out the door the exact same way. Now, this gets even more fun with this fancy new calling convention in Clang 19 called preserve none. This is super cool. So preserve none is a calling convention that has no callee saved registers. Now think about what that means. Basically, when we're making our tail calls, we are doing a lot of kind of pushing and popping and saving and restoring registers at the beginning and end of every function body. Preserve none basically says, okay, don't count on this function to basically save or restore any state. Just let it do its thing. It's going to clobber everything. What this does is it actually frees up a lot of registers for argument passing. So this is great for pinning things across tail calls, but we now have, on x86-64, we have 12 registers to play with. So the first 12 parameters that are passed to any function that uses the preserve none calling convention are passed in registers. On ARM, it's even more insane. We get 24 registers to allocate. And so this is basically a way of basically controlling the register allocation in the machine code between micro-ops, without actually having to do anything other than just saying this parameter corresponds to that register and basically treating it like that rather than needing to be more machine specific than that. So this is really, really exciting, and it's something that we're going to be looking more into for the 3.14 cycle, just because it's such an important optimization at this level. And again, we can build on top of our existing micro-op-like generation machinery, where we can use the static analysis and the DSL and our ability to generate multiple variants of an instruction in order to do this. Another thing that we hope to improve is our trace stitching. So we already do some amount of trace stitching, where basically we have several side exits corresponding to guards in the machine code, or maybe branches not taken. Those warm up over time and project traces of their own, but optimization information isn't very well shared between the parts of the traces. So we kind of lose optimization information across that stitching boundary, as well as the actual transitions themselves incur a little bit of overhead. We're doing things like jumping through function pointers and adjusting ref counts and things like that. So kind of the future that we're hoping to move forward to in trace stitching is something like this. And I'll kind of leave you with one final example. So take my state-of-the-art FizzBuzz function. It's written not too well, but it works. We're going to see how we would like to actually JIT this thing piece by piece with our tracing JIT. So I'm going to use red to indicate hot code paths and blue to indicate cold code paths. And as we JIT more and more of this loop, those paths are going to change with time. So you can see here that initially the common case is the one where we're just printing the number itself, and it's not divisible by either 3 or 5. So when we project a trace, when this loop heats up and we project our trace through the loop, it's going to look something like this. And after some light optimization, we're kind of have the basic path through the loop for this common case, which is great, but you can see here that we sort of have these side exits where we need to bail in different situations. When the iterator is exhausted, when the numbers are divisible by 3 and 5, and we need to take different code paths. One thing that we'd really like to be able to do is be able to actually sync information onto side exits. So you can see here that we have this dead store to S here that isn't actually used anywhere in this trace. However, it is just kind of a constant store. So what would be nice is if we could actually, rather than doing it here, move that store onto the 2 side exits so that it's out of the way of our main path. And so that we only actually perform that store after the fact when the time comes to actually deopt. Now, once we've done this, basically all's well and good. We're executing the hot code path using our JIT. And now we actually have kind of a different performance profile. Now the next hottest path is the one where we're divisible by 3. In this case, that side exit is going to warm up, and we're now going to project a new trace through the loop. And again, we can do the exact same thing here. However, we now have a lot more information from this sort of first pass of optimization. And since we've sunk the store to S onto the side exit, we can do constant propagation and some partial evaluation to basically reduce it to the minimum amount of work that needs to be done. Basically, just checking whether the number is divisible by 5, and then either printing fizz or syncing the store to fizz onto the side exit. And now we have the second most common path through the loop. And we can just keep doing this over and over again, where we sync this unnecessary work onto the side exit and propagate constants and do all of our cool optimizations as we work our way through the loop. And by the end of it, you'll see here that what we've actually JITted is a pretty good FizzBuzz implementation, and it's actually better than what the original code was doing. This is kind of the bare minimum amount of work that needs to be done, and because we were able to perform some relatively simple optimizations, basically our optimizer needs to know how to be able to propagate constants and add string constants together. Just by sort of sharing this information across traces, we are able to actually get something that's pretty good. And on top of this, if we are able to take all these traces that may have been compiled separately and periodically compact them into one kind of chunk of machine code, that can also result in efficiencies as well, because we won't need to be doing these indirect jumps and validity checks and all sorts of things. And once we've gotten to this point, the only thing left to do is wait for the exit from the for loop to heat up and continue projecting from wherever it happens to go next. So that's the trace stitching, and I showed here that it works for explicit control flow in the actual source code, but it also works really well for things like polymorphic code. Remember I said that our specializations will adapt to your code over time? Well, think about it. If we JIT the most common case, let's say you have a polymorphic attribute load or a method call. We'll go with a method call. So if I have a polymorphic method call, the most common one will be reflected in the specialization in the code, and we can actually inline that when we project our trace. Then, every time we call that one, it will actually stay in the JITted code, and we'll only deopt to the base interpreter, the specializing interpreter, whenever the second most common method is called, or whenever other methods are called. And soon that will specialize for the second most common method, and we can JIT a trace for that. And so we're basically relying on the specialization to not only speed up the execution of the kind of base bytecode interpreter, but also to give us this profiling information that changes with time. And we can also use it to track things like branches too. But this works for pretty much any reason why we might branch in JIT code, including weird deopt events and global validity checks and things like that. So as I mentioned, we kind of take a holistic approach. So I talked about a lot of like hardcore VM stuff here today, but there's kind of a lot of different things that we focus on our team and in this Faster CPython project in general. In general, we care a lot about our benchmarks, so we're always interested in getting new benchmarks, especially ones that use like modern code patterns or language features. We also want to reduce reference counting overhead. You notice that we were doing a ton of reference counting all over the place still. So it's tricky to do because, like I said, people still rely on the prompt reclamation of acyclic garbage, which is frustrating to say the least. But if we can prove basically through alias analysis or by knowing that we have safe types without crazy finalizers or anything like that, then we could actually start removing more reference counts because we spend a ton of time reference counting, especially in the interpreter loop. We've made some improvements to the object model over the last couple of years. Basically, most objects don't actually have a full instance dictionary until you ask for it. We kind of lie and say, oh, there's a dictionary here. If you ask for it, it'll magically appear for you. We did similar things for Python frames as well. Every frame used to be a full Python object that was reference counted and garbage collected and all of that. We now only create those on demand. So there are always opportunities to basically take these uncommon events and basically optimize for the case where they don't happen, but still have fallbacks for the case where they do. Another thing that we're excited about is what we call true function inlining. So while our tracing implementation is able to basically follow the flow of execution through a call site, we are able to propagate optimization information through that call, but we still push and pop a frame. So we don't have yet a way to actually reconstruct frames on side exits and things like that. That's sort of similar to how we would sync stores onto side exits as well. Integer unboxing is always kind of like an interesting thing. We have a lot of kind of ABI trickiness in our main interpreter loop that makes this sort of non-trivial. Pointers can escape the interpreter in all sorts of really weird ways, and people can just query Python frames almost willy-nilly, especially from like C code that we don't necessarily control. So being able to do this in a safe way where people don't just get garbage pointers is pretty tricky, and it's frustrating because it doesn't work until it does, right? We are always looking for GC improvements. So I think we spend something like 10% of our time in the GC, so small improvements there can actually have an effect on the headline number of how we're doing on our benchmarks, as well as work on concurrency and parallelism. So you may have heard there's a team at Meta that's doing a lot of really, really cool work to actually make it so Python can run with true parallelism in multiple threads. This is requiring a lot of changes to the core, and it gives us a bunch of big unknowns because while it's very much settled how to optimize dynamic languages in a multi-threaded environment, and it's very much settled how to optimize static languages in a multi-threaded environment. Optimizing dynamic languages in a multi-threaded environment is still kind of an open question. And so there's kind of a lot that we don't know there and that we're kind of curious to figure out. And who knows what else? Like, this list looked very different a year ago. It's probably going to look very different a year from now. Like I said, we're always happy to hear if anyone has ideas or wants to help contribute to this work, because the work is benefiting every user of Python. And Python is a huge code base with, trust me, a ton of inefficiencies. So thank you very much. Again, my name is Brandt Bucher. I'm at Brandt Bucher on GitHub. You can also reach me at brandt@python.org. The developer division at Microsoft, where I'm currently working, is always hiring talented compiler engineers, especially for the C family of languages. So talk to me if that interests you at all. And thank you very much. And I think we have time for Q&A. Yeah, I'll just...
Hi.
Yes, it's very quiet.
Hello. Yeah, okay.
Yeah.
So thank you for a very nice talk. I was wondering, what about if you're compiling to different ISAs like x86 or ARM and so on, is there a big performance difference there? I'm thinking especially about the number of registers, much lower in x86 and so on.
Yeah, so when it comes to register allocation, we don't have good numbers yet because we're not doing any of our own register allocation. We kind of trust the compiler to do a good job with register allocation at the micro-op level. I mean, we have a smaller number of addressable registers, but really the actual number of registers in the machine is much larger than that. So I'm actually not too worried about the number of registers. What concerns me more is actually just sort of the format of the relocations that we need to work with. On ARM, where we have these fixed size instructions that are 32 bits, splitting 64-bit loads is actually sort of a source of inefficiency. And so we might look into sort of more aggressive rewrites there when actually linking the code.
And the preliminary benchmarks that you showed, were they on x86 or ARM?
Yeah, so that's x86 Linux is usually the number that I go towards. On ARM, we actually aren't doing as well, so it's, I think, somewhere in the neighborhood of 5 to 10% slower still, and that's specifically what the people we're collaborating with at ARM are helping to work on.
Thank you.
Thanks.
Thank you. Thank you for a very good talk. So I have just a quick question. So you said memory overhead due to JIT compilation is pretty limited, but is that does it include the size of the VM itself, or just runtime memory for the code?
So that 10%, or now the 6% number that I quoted of the memory overhead is the entire resident set size of the interpreter as it's running the benchmark, so the high water mark. So basically that includes everything, including the JIT code. So we can say that the JIT code and all of its templates that we've compiled correspond to a 6% increase in runtime execution size.
That's very interesting, because most of the VM, including a JIT supporting JIT compilation, takes 10 times or 20% or more than that, 50% overhead for the memory footprint of the VM. So that's why I wonder why the system is so small.
Yeah, I think a big part of that is because we don't have a lot of de-optimization information on side exits, and once we have performed our optimizations on the linear traces, we throw them away. So for things that are doing like these de-op tables and reconstructing frames and keeping all of this metadata around, I think that's probably a huge source of overhead for more aggressively optimizing JITs. And so we may find ourselves actually having more memory overhead in the future once we start doing that. But basically right now, the increased memory overhead is purely just binary code.
Thank you.
Just as a random guess, maybe after the stack, most of the memory operations are now on ref counts.
Yes.
So do you have any optimizations to try to fuse increase, decrease reference counts on sections of code that happen to be ref count neutral, for example, swapping to variables?
Yes, yeah, so when we do our abstract interpretation, that actually gives us a nice building block for doing like alias analysis, where we know that there's a strong reference in like a local variable, so that when we push it to the stack, as long as the stack reference outlives the local reference, we don't need to actually ref count it. Deferring ref counts is something we're looking into, and that actually overlaps with a lot of the free threading work that Meta is doing, is because for obvious reasons they want to reduce ref counting on hot objects as well. And so we're all interested in different ways of actually reducing the number of reference counts, whether that's with the intent of reducing contention or with the intent of actually reducing the work itself.
Thank you.
Thanks, great work. So you've done all this sort of building a foundation for the future, and it's sort of performance neutral at the moment, so the overhead is kind of paid for. Do you have a sense of how much performance you think you can get over the next 1, 2, 3, 4 years?
Yeah, so like, again, this kind of comes back to the benchmarks. Like whenever you say, oh, we're going to be this much faster, you have to say like, okay, according to what, right? So I can show you micro benchmarks that are going to get instantly fast, basically. But what we're really interested in is our full benchmark suite. So to kind of give you an idea, that benchmark suite, for better or for worse, it represents real Python code, and it actually spends only about 1/3 of its time in the bytecode interpreter. So hypothetically, if we were to make the interpreter infinitely fast, we would see a 33% improvement, right? I think that when people talk about making Python faster, though, they're talking about pure Python code. And so we don't really have a great idea right now what sort of performance improvements we can expect. We can look to projects like PyPy or any of the JavaScript JITs to sort of see like what that kind of upper limit is. I would expect that probably our ceiling would be closer to half or 1/3 of the speedups that they're experiencing, just because we have a lot less resources to pour into making like a 6-tier super optimizing JIT, right? Yeah.
What's this XKDC CD?
I don't know, look it up.
And I have a question about your future work, the object model and garbage collection. Python has a bunch of libraries written in native code like C. So does they affect the native code? Does the object model change on object model and garbage collection affect native code?
Absolutely, yes. And so that's kind of a big difficulty in actually changing the way that like objects themselves are laid out, is because you have kind of both API and even ABI stability guarantees. So at the API level, we could say, okay, everywhere you're using a PyObject star pointer, you use this opaque handle instead, and you need to pass that to all of these library functions and don't actually access anything yourself. ABI stability is a lot more complicated because we have what's called the stable ABI, which basically says that if you compile on, say, 3.7, it'll continue working into the future without needing to recompile your extensions. And there's a lot of code out there that actually uses this. Similarly, it's really tough to play with these changes because it breaks, like our benchmarks sort of act like a canary here, where if we make a small change and a bunch of our benchmarks just start crashing, we're like, oh, this might be actually a disruptive change. So for example, to reduce the overhead of ref counting, the incref and decref macros that C extensions use are actually C macros. So those aren't something where we can actually just like swap out the implementation in the interpreter that they link against. That extension actually needs to be recompiled if we change the way ref counting works, for instance. Same with the garbage collection protocol. There's like a very clear contract of like what interfaces you need to implement and what sort of information you need to give the garbage collector, and even things like the size of the GC header on objects are things that people are implicitly relying on, whether through the ABI itself or just because they're doing weird stuff with like pre-headers and stuff. So yes, it's very, very tricky.
Thank you.
I think that the ecosystem of C extensions is a huge source of Python success, but also a huge source of frustration for those trying to make it faster.
So I want to ask a quick question. You mentioned that the relationship with JavaScript GC or JITs, and I've had the pleasure and the pain of working on industrial teams with these. And I was kind of curious if you could expand on how you see the relationship between the two. Are there unique challenges in the Python space, or is your focus more on building like developer effort efficiency? Like what's kind of like, can you just take everything that they do in JavaScript wholesale, or what's like, where's the unique challenges with Python?
Yeah, I'd say the unique challenges are both sort of at the language level and at like the, or I would say like the ecosystem level, and also just sort of like the maintenance burden itself. So we don't have a ton of resources to basically throw behind building and maintaining these huge optimizing JIT compilers, especially when we have basically a volunteer workforce of people who maybe aren't experts in JIT compilation, right? And just want to add a new language feature that people are asking for. For reference, this copy and patch implementation, people are already proposing new language features like tagged template strings and things like that. And it was kind of cool. A bunch of us were getting together at a core developer sprint, and the JIT was just automatically able to handle all their new bytecodes with no changes. And same with like being able to fix bugs, especially serious ones. Being able to make a change that fixes the bug in the base interpreter and also have the JIT and the optimizer be updated as well, it can't really be undersold for a project like ours. In terms of the ecosystem itself, we have kind of the problem of third-party C extensions, the blessing and the problem, right? Where it's like we have all these gobs of code that has been written using our ABI or has been compiled using a ABI that they expect to be stable. And so that's kind of a unique challenge for us because it really, really limits what we're able to do, especially since implementation details like ref counting and the layout of objects was leaked so early on. And then there's other things too, like for example, the free threading project is a really exciting new change to Python, but it also introduces challenges that JavaScript doesn't have because JavaScript is a single-threaded execution model like Python was for a very long time. And so I think it's kind of a combination of like language level problems, ecosystem problems, and when I say problems, I mean challenges, right? And like the actual resources that we have as a project. But like where we can look to things like JavaScript is just when kind of looking into research for just optimizing dynamic programmatic languages, there's a lot of really good stuff there. I also think it's great to look to PyPy as well, because they have a lot of the same problems we have. And I think that a lot of this sort of ecosystem stuff has been part of why PyPy hasn't been so widely adopted, even though it's a great optimizing JIT compiler and built on a really cool framework. And so I think that kind of gives us an idea of like what's worth trying and what's not worth trying necessarily.
Let me bogart one quick one now. Any security concerns about adding a JIT?
Always, yeah. If you ever want to file a CVE against CPython, it's never been easier. So I don't know if there's any security researchers. Yeah.
So you mentioned both lifting guards and like removing them opportunistically. How do you ever do that if like a user can arbitrarily jump into your for loop and you've lifted your guards out and they've set local variables and those guards are no longer safe?
Yeah, so we do have instructions that are inserted after escaping operations. So any code that could basically go somewhere that we don't manage as part of our actual trace, we basically perform a quick check on a flag after every single one of those calls has returned. So that could be something as kind of annoying as deroughing a reference, since that could have a finalizer, or something as routine as just calling out to a C extension that we don't control. So basically, if they invalidate the world, we just have a quick bit that we check that will basically just exit the JITted code and sort of fall back on the interpreter. And so that's sort of how we maintain our sanity, is by assuming the world hasn't changed all over the place and making it very, very fast to check when it has.
Yeah, I agree that developing a new modern benchmarking is significant. I suppose that nowadays most runtime time is spent in the library like a NumPy. So I wonder, how much impact you expect by JIT compilation of pure Python code, because it's Python code is used as a kind of scripting language nowadays. So, well, in a worst case scenario is that, even if you develop a nice JIT compiler, the total execution time might not very much change.
Right.
What do you think about that?
Well, I mean, our goal is pretty clear. Our goal is to optimize the single-threaded execution of pure Python programs. So whether that affects you significantly will depend if you're spending 90% of your time in a NumPy, operations, or in code that's JITted by Numba or TensorFlow or whatever else. What we can do is we can kind of smooth out the edges. So if we can make it easier to call to and from NumPy, for example, by basically providing easier API boundaries, or by allowing them to, for example, register specializations when they're loaded or things like that, then it becomes a little easier. And kind of our hope is that moving away from heavy things like NumPy, our hope is not to move away from heavy things like NumPy, but like shifting the conversation away from heavy things like NumPy. One thing that we've observed is it's actually frustrating to sort of project our traces when there's just gobs of C code in between that just kind of break up our traces. And so what we feel like we're moving towards is where previously a lot of code, like small utility functions, would be moved out of Python and into C for performance. We're already starting to see that that may be a kind of less of an attractive option, which kind of shows that we're on the right track. There was at least one or two projects that had some accelerators in C that they found were actually a lot more performant once we landed the specializing interpreter, just to leave in Python code. And for simple utilities like, for example, the any and all functions, min, max, a lot of these built-ins that are implemented in C might benefit from having pure Python implementations that we could inline more aggressively.
Thank you.